Hello, my name is Jack Wellman, and I'm Director of Program Development for Airmanship Incorporated, the knowledge center for today's pilots. You will note that our title states that these tapes are designed for the non-professional professional pilot. Although that may sound somewhat redundant, we don't intend for it to be that way, and let me explain. One concept most of us have about the word professional is an occupation for which a person receives compensation. We speak of professional truck drivers or professional actors or professional educators as people with training and experience in their chosen career field. Another concept of the term professional, which has developed over the years, is that of the person who really knows what he or she is doing regardless of whether or not it falls within that person's chosen line of work. Have you heard someone say, take your TV to Bob Davis? He's a real pro when it comes to repairing television sets. Or how about the neighbor who's been audited by the IRS 4 times and has come out clean each time? Now that's a real professional, even though the guy drives a bus for the local transit line. Airline and corporate pilots, for the most part, qualify as professional pilots. They not only earn their living at flying an airplane, but they study airplanes and how the airplanes fly. The company they work for usually requires them to go to school periodically, a school like airmanship. Most of them know everything about the plane they fly, and they have a thorough knowledge of how most airplanes fly. Many of the pilots who ask airmanship for training are not professional pilots. The airline pilot has his training taken care of by the company, but the people who come to airmanship want to be professional pilots, as in the second definition of the word we presented. Many of our students earn their living doing something other than flying airplanes, but they would like to be a real pro when it comes time to fly their own planes. So this course is designed for many of you, the pilot who has a career but who wants to know his own aircraft better and wants to have the professional pilot's knowledge of how airplanes fly. The topic of aerodynamics is a technical one, filled with jargon, formulas, and graphs. Although I can't completely separate myself completely from all of that, I will limit as much of the highly technical stuff as I can, and will stick to the basic concepts. In this first tape, I will revisit with you some of the areas you studied when you were first learning to fly. We will discuss the atmosphere, its composition, and its properties of pressure, density, and viscosity. Next, we will examine the 4 forces which act upon an aircraft in flight. We will look at an airfoil, name its parts, and establish terminology important to understanding the generation of lift, such as angle of attack, camber, angle of incidence, and chord line. The principles and laws and Bernoulli will be explored along with the theory of circulation. As a result of this, the relationships among camber, relative wind, and angle of attack should be well established in your mind. Except for scientists who study it or environmentalists concerned about its quality, most people give little thought to the air which surrounds them. But if you're counting on it supporting you immediately after rotation from the runway, you should reacquaint yourself with it. Almost everyone remembers that dry air is 78% nitrogen, 21% oxygen, and 1% other gases. The ratio of these gases remain the same around the world and as high as the atmosphere extends. Water vapor is also a gas found in the atmosphere. Its quantity may vary, unlike the other gases whose ratio is pretty well constant. It may make up from near 0% of the atmosphere to a maximum of about 5%. As the amount of water vapor increases at a given point, all other gases are reduced proportionately. When water vapor is absorbed by the atmosphere, it reduces the molecular weight of the air. It makes the air thinner, so to speak, because a molecule of water vapor is actually lighter than a molecule of air. It seldom affects aircraft operation by itself. The total amount of water vapor, even at saturation, is too small for that. However, in a takeoff requiring maximum performance, the amount of humidity in the air may be an overlooked ingredient which could take years off a healthy person's life. Most of us probably know that, that air is a gas, and as such has all the properties of gases. It has mass and weight. It can exert pressure. It can be compressed or diffused, causing changes in its density. And it can be liquid. It offers resistance to objects moving through it. All of these properties are at work when you fly your plane through the atmosphere. Let's first look at the word, or the words, static pressure. Remember the 14.7 pounds per square inch you learned in junior high school science? That was supposed to be the normal air pressure? That is static pressure. You probably remember a specific number without any qualifications. However, the figure is an arbitrary one and only pertains to sea level on a, quote, standard day, unquote. If you went to school in North Platte, Nebraska, the figure that you learned as normal air pressure was about 1.5 pounds per square inch off. Air pressure on a standard day in North Platte is more like 13.2 pounds per square inch. Static pressure, then, is the force exerted by the weight of the atmosphere pressing down from hundreds of miles in space. It is pressing down because it has mass and is reacting to the pull of gravity. If that is so, why isn't the pressure equal regardless of the altitude? Why does North Platte, at a little over 2,800 feet, have over a pound of pressure less than at sea level? One of the other properties of air helps us to explain it. Compressibility was mentioned earlier. The more weight exerted upon a gas, the more dense it becomes. A column of air 1 foot square, extending out to the limit of the atmosphere, weighs a little over a ton at sea level on a standard day. For each minute measurement upward, away from the Earth, there is less weight pressing down. This means that the atmosphere at that point is a little less dense. The higher we go from the Earth's surface, the less weight there is above us. There is less pressure of the gases in the atmosphere, and the pressure exerted becomes less. With less pressure exerted on it, the remaining air takes up an ever-increasing volume. Researchers have pretty well established that about half the atmosphere exists below 18,000 feet, while the upper half continues out for hundreds of miles into space, simply to fade away into immeasurable amounts. Before we leave static pressure, I'd like to point out that we have been discussing it on the basis of a standard day. A standard day rarely happens. It's simply a norm based on weather observations over many years. We all know that the atmosphere is in a constant state of turmoil, with huge mounds of air piling up in places, leaving other spots with a thinner layer of air above them. Therefore, our definition of static air pressure is the pressure which results from the mass of air supported above it at the altitude or elevation from which the measurement is being taken. I've made reference to density, so let's discuss that next. It is simply the amount of mass in a cubic measure. For example, air under standard sea level conditions weighs 0.0765 pounds per cubic foot. At 10,000 feet, a cubic foot of air would weigh only 0.0565 pounds. This means that close to the Earth, there is a great many more molecules in the air in a given measure than in a comparable measure at a higher altitude. Unlike solids and liquids, gases have the ability to change density by great amounts in a short period of time. In our atmosphere, these are due primarily to the varying amounts of heat which the atmosphere is subject to around the Earth. Air density varies directly with pressure and inversely with temperature. Although the density of the atmosphere is greatest at sea level due to the weight of the atmosphere, it will become less dense as it is subjected to high temperatures. The air also has a property called viscosity, as do other gases and liquids. Now, most of us have heard the term and think of oil we put in an engine when we hear the word. The numbers on the can tell us something about the oil, but not really its thickness, as is it's a common assumption. Viscosity is the tendency of an air or liquid to cling to an object and to itself. It possesses the qualities of adhesion and cohesion. It is somewhat like the wad of bubble gum you step on from time to time. It wants to stick to the ground, but it also wants to stick to your shoe at the same time. And it wants to stick to itself, and in so doing stretches out to a breaking point. Air is similar to the gum as it rushes past your aircraft or your car for that matter. Because of viscosity, there is a boundary layer of air adjacent to the wing's surface which is less than an inch thick in most cases. It affects how efficiently your plane flies. Viscosity is not the most important concept in aerodynamics, but is one you should know about. Dynamic pressure is one of the most important concepts in aerodynamics. It is air pressure created by movement of air. Aerodynamically, it represents the kinetic energy of the free airstream. It is determined by density and velocity. Dynamic pressure varies directly as the density and as the square of the velocity. In other words, if density is decreased by 1/2, the dynamic pressure would be decreased by 1/2. However, if the velocity of the airstream is doubled, the dynamic pressure would increase by 4. Let's take a look at a chart which represents a standard day, one of those we mentioned earlier. This illustration is an excerpt and not the complete chart, which was originally put together by the National Advisory Committee for Aeronautics, the predecessor to NASA. The chart is based on many years of weather observations, and since it was published has been confirmed as basically accurate. Its purpose is to provide a common denominator for the measurement of aircraft performance and to provide a standard upon which to calibrate and correct the readings of some aircraft instruments. The chart will be important when we discuss aircraft performance and in other presentations dealing with instruments. Before dealing specifically with any one of them, let's take a moment to review the 4 forces acting on an airplane in flight. You know them as thrust, drag, lift, and weight, or gravity as some prefer to call it. The 2 forces which are constantly trying to bring you to a stop on the ground are drag and gravity. The 2 forces which you must produce to overcome these negative forces are thrust and lift. Thrust must be able to overcome drag, and lift must be able to overcome gravity before the plane can get off the ground. In a stabilized flight condition such as level flight, climb or descent at a constant velocity, thrust and drag are equal and lift and weight are equal. The propeller is producing a given thrust, but the total drag equals that thrust and limits the speed of the aircraft. The weight of the plane plus a little extra aerodynamic weight is equaled by the lift produced over the wings. In aerodynamics, this stable condition is known as equilibrium. What happens when the throttle is advanced, increasing the power? Well, the plane will accelerate until drag, once again, is equal to the total thrust, and the speed will stabilize at a new setting. The plane will climb due to an increased relative wind over the wings. Once the new rate of climb has been established, lift and weight will again be equal, and the plane will climb until the factor of air density degrades performance enough to stabilize it at a new altitude. Now that was brief, but I just wanted to reactivate the image of the 4 forces which have probably been dormant in your subconscious for quite some time. Before we leave it to go on to a deeper study of lift and drag, let's look at why some texts refer to weight and some to gravity. Now, the noted author Asimov explains weight as a force with which a body is attracted to the earth. In other words, it only acts in one direction, toward the center of the earth. Using the word weight in that sense would never allow an airplane to weigh more than 1 g. Now, if you've flown a plane for very long, you know that there are many times when your arms have felt so heavy that they could hardly leave your lap. What has happened is that other forces, such as centrifugal force, have combined with weight to make it seem as though you and your plane are heavier. The aviation community has adopted a scale to express this combination of forces. It's called G-forces, and its units are in multiples of the plane's weight. 2 G's are twice the loaded gross weight of the plane. Positive G's are always directed toward the bottom of the plane, regardless of its attitude, and G's are directed towards the top of the plane. It is these G forces that lift must oppose, and not simply the weight of the plane. Now we come to the big question. What is lift, and how is it produced? Before we get the answer, let's look at some pictures and review some more terms. An airfoil is any part of the plane shaped so that it responds to air movement by producing differential pressure on either side of the airfoil. The wing, propeller, and empennage are the important airfoils. Leading and trailing edges of the wings seem to be pretty obvious, but they do more than just outline the silhouette of a wing. Their location has much to do with the aerodynamics of an airfoil. A line connecting the leading and trailing edges of an airfoil is referred to as the chord line. It should not be thought of as being a permanently anchored thing, since it moves as the high lift devices change the shape of the wings. Its position in relation to the relative wind and the longitudinal axis of the aircraft are extremely important. Camber means curving or bending. On an airplane, it refers to the curving surfaces. A wing which has identical curvature top and bottom is known as a symmetrical wing. An asymmetrical wing usually has a flatter lower surface with more curvature on top. Relative wind is the airstream created by the movement of the plane through the air. Most of the time, its direction is opposite the flight path of the aircraft, but it may be deflected by gustiness or wind shear. Angle of attack is the angle between the relative wind and the chord line of an airfoil. Increasing the angle of it will increase lift and also drag. It also determines the point at which a wing will stall. A given wing will always stall at the same angle of attack, regardless of speed or attitude. It is rare that a manufacturer fits a wing to an airplane so that its chord line is parallel to the longitudinal axis of the plane. In normal cruise flight, they want the fuselage to be parallel to the ground, but it must be able to support maximum gross weight at the same time. Therefore, the wing is set into the plane at what is called the angle of incidence. This provides just enough angle of attack so that the pilot should not have to trim beyond a neutral position. The generation of lift is based on the Bernoulli principle, which in turn has its basis in the law of the conservation of energy. Let's look at this diagram of a tube with a restriction at midpoint. At point A, the potential energy is represented by static pressure. When the air flowing through the tube reaches the restriction at point B, it doesn't just pile up, it speeds up. The increase in velocity at point B means that some of the potential energy has been converted to kinetic energy. The law of the conservation of energy requires that total energy in the tube remain the same. Therefore, we have taken from the potential energy to create some kinetic energy. Since we said that potential energy was represented by static pressure, we have reduced the static pressure by using some of its potential energy to create greater velocity at the restriction at point B. After the airflow passes the restriction at point B, its velocity decreases and the pressure increases. If the velocity at point A and C are the same, then the pressure would be identical. Another important concept in the generation of lift is circulation. If you are a baseball fan, you probably have seen its effect on a pitched fastball. Look at this diagram of a cylinder and an airflow. We will ignore density and viscosity at this point. Note the pattern first where the cylinder is stationary, and in the second illustration where the cylinder is rotating. The circulation of the cylinder has produced not only a larger amount of lift on its top side, but it has also produced an upwash ahead of the cylinder and has moved the stagnation points toward the bottom. There are normally two stagnation points on an airfoil. They occur along the leading and trailing edges of an object placed into an airstream. At the leading edge, where the air separates to go either above or below, a small area exists where there is no air movement. At this point, a stagnation pressure develops, which is the sum of the ambient pressure ahead of the wing and the dynamic pressure around the wing. A similar area occurs along the trailing edge of the airfoil. Apply this concept to baseball. The pitcher puts some topspin on the ball as he throws. The highest velocity exists over the top of the ball, creating lower pressure there than on the bottom. This lifts the ball. It actually bobs up from the plane in which it was thrown. And if it's a good fastball, the batter will undercut it completely. Back to airplanes. Compare the cylinder diagrams with two diagrams of a symmetrical airfoil. Note how similar the illustration of the airfoil at zero angle of attack is with the non-rotating cylinder. There are stagnation points fore and aft, and reduced pressure is equal top and bottom. Now look at the diagram where the cylinder has been placed in rotation. Lift forces on the top, where velocity is greatest, has increased, while the opposite is true on the bottom. The stagnation points have moved to a lower position. The net result is a positive force acting perpendicular and upward from the cylinder. The position of stagnation points is of additional importance to you. It is the leading edge stagnation point that has the area where ice formations start. Because of the stagnant air at this point, the ice sometimes develops almost a horn shape, which continues to build out beyond the stagnation area under some circumstances. The symmetrical airfoil, tilted to a positive angle of attack, shows very similar pressure patterns. Note also the upwash ahead of the airfoil and the downwash behind the trailing edge. The airfoil appears to have the same circulation around it as does the circulating cylinder. This helps explain why velocity of the airstream over the wing accelerates as the wing is placed in motion. It is subject to the same type of circulation. One more observation deserves our consideration. The symmetrical airfoil at small angles of attack may develop negative air pressure both top and bottom. It will be true, however, that the least pressure will still be on the top of the wing. It is also true that at high angles of attack, the pressure on the surface will be increased. It will force large quantities of air down in the downwash coming from the airflow over the top of the wing. In this situation, up to 1/3 of the lift force may come from the increase in pressure. So far, I have presented you with three important concepts on the production of lift. First, the Bernoulli principle utilizes the theory of conservation of energy, and it explains why air placed in motion over an airfoil reduces the pressure. Second, the theory of circulation helps us to understand why the velocity of air flowing over the wing is greater than that flowing beneath the wing. Third is Newton's third law, which states that there must be a reaction for every action. We know that large quantities of air are forced downward behind the trailing edge of the wing. If we force air downward, the reaction in nature is to force the wing up. Now that we know why lift is produced over the wing, let's take a look at how engineers determine the amount of force produced by this phenomena. It will involve a mathematical equation, but not one that you should find very intimidating. The formula for lift looks like this. Lift equals the coefficient of lift times 1/2 of the density times the velocity squared times the wing surface area. All of the items seem obvious except coefficient of lift. This item is an index number representing the ratio between lift pressure and dynamic pressure. It is related to the shape of the wing, and the angle of attack. The maximum lift coefficient for any wing occurs at the point of the stall. We know that a wing will always stall at the same attack. We therefore reach the maximum coefficient and the stall angle of attack at the same time. This has implications for landings and takeoffs. For illustrative purposes, let's place two aircraft on a runway side by side. All factors are equal except the maximum coefficient of lift. Airplane A has a maximum coefficient of lift of 1.8 with a thick asymmetrical wing, while B has a thin symmetrical wing with a coefficient of 1.0. Which plane will use less runway for its landing and takeoff? It will be the aircraft with the highest maximum coefficient of lift, or in this case, aircraft A. Now, would it be possible to modify airplane B without changing to another airfoil and be able to equal the landing and takeoff performance of airplane A? Yes, it would. We could cut loose a section of the wing at the trailing edge and hinge it so it would kind of droop down. Why don't we call it a flap? Since shape is considered in our index, we bend the flap down until we get a camber which will be equal to 1.8 as its maximum coefficient of lift at the maximum angle of attack. Now, we can use the same landing and takeoff figures for both aircraft. Additionally, we can retract the flaps while in cruise and have the benefit of a cleaner airfoil with less drag. The lowered coefficient of lift will be compensated for by increased speed. This chart was taken from Aerodynamics for Naval Aviators. It shows that the coefficient of lift varies directly with the angle of attack. How is it possible that a diminishing angle of attack and a lower coefficient of lift can keep an aircraft in the air? The answer is your airspeed. Note on the line, which correlates index numbers and angle of attack, that selected airspeeds are also given. You will find that as the angle of attack and the coefficient of lift diminish, the airspeed increases. Many instructors use this information to demonstrate that control of airspeed is primarily a function of angle of attack. They further claim that power is used to control altitude. Although discussions on this topic have appeared in the journals from time to time, it is well accepted that attitude controls airspeed and power controls altitude. Well, we ought to regroup here for a moment. We have just determined that there are basically three things which determine how much lift you will get over your wings. They are relative wind, angle of attack, and camber. They are interrelated so that what affects one has an effect on another. For example, let's take a plane in straight and level flight. If we retarded the throttle and began to lose altitude, you would automatically adjust the angle of attack if you wish to remain in level flight. This would reduce your airspeed, but by increasing the angle of attack, you have increased the coefficient of lift, which gave you the lifting force you need to remain at a given altitude. There have been many pilots who have lost airplanes because they didn't understand this relationship. Take the full flap go-around as an example. Cleaning up flaps means reducing the coefficient of lift to that of a clean wing. Getting rid of flaps all at once without giving the plane a chance to accelerate and compensate for this loss may mean a stall and most the loss of altitude at a crucial point. The FAA often states that the stall spin accidents are the most common type of fatal accidents. All pilots learn early in their training how to make an airplane stall. Instructors point out to them through movies and diagrams how the air burbles after the critical angle of attack has been reached. However, people still have stall accidents in disturbing numbers. It is important in any discussion of aerodynamics that we review stalls. We will start with airflow around a wing at zero angle of attack. When we do this, you must remember that we have sliced off one cross-section of the wing. other patterns of airflow will be occurring at other places around the wing at the same time. The ideal situation would be for the airstream to flow smoothly around the camber of the wing's layers. This is referred to as laminar flow. Most wings start with laminar flow at the leading edge, but it is converted to a turbulent flow toward the trailing edge. Just aft of the forward stagnation point, a boundary layer is formed in the laminar flow. Because air has viscosity, it wants to cling to the wing surface where its velocity theoretically is zero. It also starts to hang together like the bubble gum mentioned earlier, so that it tends to hold the boundary layer to the wing. Within the boundary layer are velocities ranging from zero at the wing surface to the velocity of the dynamic air in the main layers of the airstream. The boundary layer is usually only a fraction of an inch thick. Somewhere behind the point of maximum thickness of the camber, the airstream cannot hold to its smooth boundary layer. It becomes turbulent. As long as it has a strong enough velocity, it will remain layered. Stagnation pressure from the trailing edge of the wing is quite powerful. The velocity of the turbulent layer diminishes as it nears the trailing edge, and the airflow along the wing may actually reverse direction due to the trailing edge stagnation pressure. What would cause the turbulent layer to lose velocity? When the angle of attack is increased, it becomes more difficult for the boundary layer to cling. The circulation effect produces an upwash at too great an angle over the leading edge. This allows the turbulence layer to spread toward the leading edge. Because it is turbulent, its velocity is decreased, and the trailing edge stagnation pressure amplifies the airflow separation. At the stall angle of attack, this separation is complete. All you have left to keep you in the air is the downward deflection of the air from the bottom of the wing. Unfortunately, some training manuals leave you with just the images of the wing sections and their airflow patterns. Well, a wing just doesn't behave that way most of the time. First, it is designed so that its stall pattern follows a known progression. A well-designed wing will stall first at the trailing edge near the wing root. Except for the T-tail aircraft, this places the tail surfaces in turbulent downwash, which produces the buffeting that is your warning of an impending stall. It also leaves the tips to stall last, which gives some degree of aileron control up to complete stall. It also helps prevent the plane from developing some nasty wing drops to stall, which could happen if the tips stalled first. Your wing may still be flying when the stall breaks. The reason the nose falls through the horizon with suddenness is that there is a complete stall close to the fuselage, which eliminates the downwash over the horizontal stabilizer. Your plane depends on that downforce to balance a nose-down pitch built into it at the factory. With the tail force gone, the pitch force takes over and drops the nose. By stalling the wing root area first and having the stall progress outward from the fuselage, the pilot is given a warning of an impending stall. The nose will automatically pitch downward toward recovery, and aileron control will exist well into the stall, but not after a complete stall. The way that designers get the wing root to stall first is usually to twist the wing by giving it a smaller angle of incidence at the tip than it has at the root. It is only a matter of a couple degrees, but it does the job. It is also possible that the airfoil near the tip is of a different shape than the airfoil in the main wing section. If the coefficient of lift is higher at the tips, it will mean that the tips will remain flying after the main wing has stalled. Another technique in inducing root stall first is to place a small triangular strip on the leading edge near the wing root. At high angles of attack, these strips disrupt the smooth airflow over the wing enough to induce early airflow separation and will initiate the stall at that point. A point worth repeating concerning stalls is that they can occur in any aircraft attitude and at any airspeed. A snap roll at the top of a loop when the plane is inverted is a stall maneuver. High-altitude aircraft cruising just under Mach 1 have stalled in clear air and have fallen thousands of feet before recovery. The angle of attack at which a given airplane will stall is always the same. Your stall warning device is set to trigger at a few degrees below the stall angle of attack. Remember that the next time you make a tight turn from base onto final, believing that just a little extra airspeed will compensate for the higher angle of attack needed to support the airplane. During the discussion on the forces of weight and lift, I mentioned that your aircraft will be called upon to support more than its loaded gross weight on occasion. This will occur when extra G-forces are experienced and can happen during a maneuver as simple as a turn into the pattern. At the other end of the scale would be the upgusts in, say, severe turbulence. Lift must support the total weight of the plane. This means that if your plane weighs 3,500 pounds and is in a turn pulling 1.3 Gs, the total aircraft weight which lift must support at that moment is 4,550 pounds. If you increase the angle of attack to produce the extra lift necessary, the plane will slow down. It is easy to see that angle of attack by itself cannot compensate for total weight of the aircraft under some circumstances. It will be necessary to add power in order to keep below the stall angle of attack. The high lift device you are most familiar with is the trailing edge wing flap. I discussed with you earlier how you could increase the coefficient of lift on a wing by lowering the flaps. Some aircraft have been modified so that the ailerons droop as much as 15 degrees with the flaps and still operate as ailerons. This gives the plane full span flaps, which increase takeoff and landing performance considerably. Modern aircraft are equipped with any of four types of flaps. They are the plain flap, slotted flap, split flap, and Fowler flap. Their primary purpose is to allow for steeper landing approaches by increasing the coefficients of lift and drag. Many general aviation aircraft use a version of the plain flap, which is essentially a section of the trailing edge which can droop to, say, around 40 degrees. The slotted flap is related to the plain flap. The difference is that the flap is pushed back away from the wing as it comes down. This allows high-energy air from below the wing to be ducted over the flap. The renewed airstream gives the boundary layer the velocity needed to delay airflow separation longer, which increases the coefficient of lift even more. A close look at a Cessna high-wing airplane will give you a good picture of this type of flap. The flap used on the Goonie bird, the legendary DC-3, is called a split flap. In this type, just the lower surface of the wing droops down instead of the entire trailing edge section. Its coefficient of lift is slightly better than the plain flap, but it produces great quantities of drag. The Fowler flap not only droops to change the camber, it also uses a portion of the undersurface of the wing to increase wing area by sliding it aft as it is lowered. The total wing surface is one of the prime factors in the lift formula. A flap which can increase the coefficient of lift and at the same time increase wing area will greatly to the lifting force. That is what the Fowler flap does. However, it needs a complicated mechanism and some pretty heavy hardware, which makes it expensive to install on the average general aviation airplane. High-performance aircraft will often include lifting devices on the leading edges as well as the trailing edges. Here's why. Earlier, we discussed how the boundary layer converted to a turbulence layer slightly aft of the point of maximum wing thickness. With flaps down, the turbulence layer tends to separate from the surface more readily. The boundary layer needs a dynamic shot in the arm, and that is provided by opening a contoured slot along the leading edge of the wing which allows the boundary layer to pick up enough momentum to delay the onset of the turbulence layer, which improves the coefficient of lift. The movable slat is the most common leading edge high lift device. It is either automatically operated by the airflow or operated manually by the pilot. In addition to allowing for a smoother airflow over the wings, these leading edge slats or flaps also change the camber of the wing and improve the coefficient of lift. It was the automatic retraction of the leading edge flap on the left wing of the DC-10 in Chicago which caused the wing to stall, rolling the aircraft out of control. Experimentation continues with devices designed to control the boundary layer for the full width of the wing. The engineers have been quite successful with boundary layer control, but have yet to figure how to eliminate the miles of plumbing necessary to make it work. The two major systems either bleed air from the surface through hundreds of tiny holes to a suction pump, or force air through the holes from the compressor section of the cabin engine. Either way provides the aircraft with a new, higher stalling angle of attack. Although results have been good, the cost-benefit ratios have not yet been positive enough to put it into production models. We have now scratched the surface of aerodynamics by helping you understand perhaps a little better the concept we call lift. We know it is a direct product of properties and conditions which prevail in the atmosphere. Static and dynamic pressure, density and viscosity of the air around us determine conditions for the production of lift. We have dissected a cross-section of the wing and named its parts: leading and trailing edges and chord line. We have defined and differentiated between angle of incidence and angle of attack. We discovered how a wing produces lift by examining the theories of Bernoulli, dealing with the conservation of energy, of Newton, dealing with action and reaction, and the theory of circulation, explaining increased velocity over the wing. We discussed relative wind, camber, and angle of attack. Stalls were revisited and expanded upon. Finally, we discussed high lift devices and how they affected the production of lift. Generating lift over the wing of an airplane would be simple if we could stop right here. However, we have already gotten involved with drag on several occasions, and drag deserves some time of its own. So right now we will terminate our present discussion. To continue with us in this airmanship series of tapes on aerodynamics, you should go next to the tape entitled The Development of Drag. Welcome back to Airmanship series of lessons on aerodynamics. My name is Jack Wellman, and in this session I will take up the subject of the development of drag. Before I go any further, I would like to remind you that this tape is the second in a series. Aerodynamics is developmental, so you should have worked with me on the generation of lift, our first presentation in this series, as a prerequisite. If you have not worked on lesson 1, the generation of lift, remove this cassette from your VCR and replace it with number 1. Before I plunge into the elements which determine drag on an aircraft, let's look briefly at what we did in our first presentation. We'll be dealing with all the properties of the atmosphere which affect the generation of lift. Let's take 30 seconds to write down a list of them. Your list should resemble this one. Atmosphere has mass and weight, exerts pressure, can be compressed or diffused, can flow like a liquid, and offers resistance to objects. Now pause for another 30-second break and create a new list. This time list all the terms we used in connection with the generation of lift. Most of the terms you will have on your list would be as follows: airfoil, chord line, relative wind, angle of attack, angle of incidence. Our discussion of lift was based on three well-accepted scientific laws or principles: the Bernoulli principle, Newton's third law, and the principle of circulation as it pertains to a rotating cylinder in a free-moving airstream. We will refer to these again in this presentation. Lift equals the coefficient of lift times dynamic pressure times wing surface area. That is the equation used to calculate total lift produced by a wing. Keep in mind that the coefficient of lift is a dimensionless ratio between the lift pressure and the dynamic pressure. Think of it as a measurement of how efficiently a particular airflow generates lift at various angles of attack. In this presentation, we will be dealing with the drag coefficient, which I will have more to say about later. The other two topics I dealt with in tape 1 were stalls and high lift devices. I have divided aerodynamics into several topics for the sake of study. Be aware that everything I describe in these tapes is going on all the time and at the same time. The atmosphere becomes a very busy place once you place an airfoil in motion through it. Now, we all know drag opposes thrust. It goes to work as soon as the air starts to move the airframe. It's always with us as we fly, and we even make good use of it at times. As pilots, we can't do anything about most of it, but we do have some control over one type. Most of us learned that there are two types of drag. They are parasite drag and induced drag. You buy parasite drag with the airplane. Its design and general condition will determine how much there will be. Induced drag is a product of lift, and this is where you can exert the most control. I will take a parasite drag with you first, and we will see what we can do to keep it to a minimum. It has several subdivisions, which we will look at one at a time. They are form, skin friction, interference, separation, pressure field, power plant, and wing section profile. Form or flat plate drag is sometimes referred to as the barn door effect. It is created by the total frontal area of the plane and includes not only the fuselage, but gear, struts, wires, and antenna as well. Many ultralights have large quantities of form drag, part of which is the human body hanging below the wings. Skin friction drag is created by the rubbing of the air molecules against the total exposed surface of the plane. It is directly proportional to the amount of surface and the roughness of the surface. Many home-built planes made of composite materials can be rubbed to a super smooth finish, thereby eliminating a good chunk of skin friction drag. There is a tendency for the airflow to break down and separate wherever an appendage meets the fuselage. This creates what the engineers call interference drag. Some of this type of drag can be eliminated by placing streamlined fairing where the wings, landing gear, struts, and etc. meet the fuselage. Separation drag is interference drag in that it is the result of design problems. It may occur wherever there is an abrupt contour change in the fuselage shape. The switch from the straight razorback fuselage to bubble canopy on some of the World War II fighters, such as the Spitfire, P-47, and P-51, caused a breakdown over and around the tail surfaces, necessitating the addition of a ventral fin ahead of the regular vertical fin. While the ventral fin did not totally compensate for drag, it did restore directional stability. Whistling doors are a clue to the fact that you may have what could be referred to as pressure field drag. It occurs around leaky doors, cowlings, and all control surfaces. You can install new door seals and tighten up cowlings, but the leakage around the control surface is a design problem that modification or redesigning may take care of. Power plant drag consists of the energy used in cooling the cylinders, providing ram air to the carburetor, and driving accessories. Cowl flaps allow for adequate cooling during ground operation and high horsepower maneuvers, but are closed in cruise to eliminate some of the power plant drag. In selecting the airfoils which will be used on a particular aircraft, the engineers must be concerned with wing section profile drag. Section profile means that the airfoil shapes taken from cross-sections of the wing at various stations are being considered. The designer must consider such things as the ratio of maximum thickness to chord. At what point along the chord will the maximum thickness occur, and what kind of curves will be used. This information is not only important in determining the coefficient of lift, but also of the section profile drag. The ideal airfoil section would have a high coefficient of lift with a low profile section drag. Since this is an impossible design to come up with, every section airfoil is a compromise. It's further compromised by other considerations such as the thickness of the main spar and whether flaps or ailerons will be part of that airfoil. In summary, wing section profile drag is extremely important to the aircraft designer in establishing the efficiency of the wing for a particular aircraft. Total drag consists of all these parasite drags plus induced drag. Your control over parasite drag consists mainly of keeping your plane clean and waxed and sealed up tight. You do have some control over induced drag, so let's talk about that. Placing a wing in motion produces both lift and induced drag. It's like having a date with Siamese twins. If you take one, you have to take the other, regardless of how ugly the other one might be. We look at lift as being the desired twin and drag the ugly one. I'm sure you've heard an unpleasant date partner described as a drag, but we know that one must look deeper than the epidermis to discover all the qualities of a person. Maybe we can apply this to induced drag as well. I'd like to go back to the circulation theory dealt with in the lift tape. The next three diagrams will illustrate how induced drag is produced. I've taken a few technical liberties with them and have incorporated some slight exaggerations, but they are basically true representations. In diagram 1, we show a hypothetical situation of level flight with a neutral angle of attack and an asymmetrical airfoil. In order to remain, lift must equal weight. The lifting force opposing weight we will call effective lift. It is blue in color. In this situation, the effective lift is equal to the total lifting force of the wing. Total lifting force is red. Before we go to diagram 2, a word about average relative wind. In basic aerodynamics, you learn that wind is always opposite and parallel to the path of the plane. This is true of the main airframe, but not always true of the wings. A moment ago, I mentioned the circulation theory and pointed out how air sweeps up ahead of the wing and produces a downwash behind it. The circulation of air creates a slightly different relative wind for the wings, which is usually inclined upward from the path of the plane. As the angle of attack increases, so does this average relative wind. You have been told that your plane will always stall at the same angle of attack. As you demonstrate a stall on your next biennial flight review, observe the angle made between your wing chord line and the horizon. You know your wing is supposed to stall at maybe 18 degrees, but you are observing 30 degrees. This is because the wing's average relative wind is at a much higher angle than the relative wind for the plane as a whole. In diagram 2, I have introduced a small angle of attack. Note that the average relative wind is also slightly inclined to horizontal. We are still in level flight, so the weight and effective lift are equal and opposite. However, the total lifting force of the wing acts at 90 degrees to the average relative wind. it is now inclined aft and has become greater than the effective lift. The significance of this is that some of the total lift force is now acting toward the rear. It is opposing thrust, so must be classified as drag, induced drag to be specific. How much induced drag is being produced in this instance? We can find that by measuring the distance between the tips of the red and blue arrows. In diagram 3, we have further increased the angle of attack and the average relative wind. Note that the total lift force is at a much larger angle to the effective lift vector and is longer. This situation produces more space between the arrow tips, indicating greater induced drag. Although it may not be completely obvious from our diagrams, the conclusion is that induced drag not only increases with an increased angle of attack, but it also increases at a greater rate than the angle of attack. This is the diagram we used, and you can see that the relative wind for the aircraft sweeps up just before it gets to the leading edge of the wing. As it passes over the wing, a downwash develops and continues behind the trailing edge of the wing. We're not through with induced drag just yet. So far we have dealt only with idealized cross-sectional diagrams of wings. If we put the whole wing together, we will see that the dynamic air does not seem to follow as simplistic a path as in the previous diagrams. The air currents flowing over the wing will take a diagonal path leading toward the fuselage. The currents under the wing will move diagonally toward the tips. Why is this so? It is the nature of liquids and gases to try to fill in any weak spots or holes. We know that the area over the top of the wing has something less than the ambient air pressure. We also know that the air pressure beneath the wing is a bit greater than ambient air pressure, and the higher pressure will try to fill in the area of the lower pressure. Since the wing blocks the passage except for the tips, there is a movement along the bottom of the wing toward the tip. Once there, the air spills up and over, creating a vortex which trails behind and below the tip of the wing. The curling of the air currents over the wing at the tips produces a force which causes the air to be deflected toward the wing roots on the upper surface of the wing. All wings presently flying have tips which produce some amount of vortex. In a vortex, the downwash is greater than the upwash. This situation creates a higher induced angle of attack, which in turn creates higher induced drag. The heavier an aircraft becomes, the slower it flies, the greater the vortex becomes. This means that induced drag is greatest as your plane approaches its level flight stall speed. From your first lesson to your last approach, you have been continually warned to be alert for wake turbulence. Right now you can probably visualize those twin tornadoes trailing from the tips of a 747. They will drop 800 or 900 feet, level off, and begin to spread apart. Perhaps you have been warned about the big planes so much that you aren't prone to visualize these same tornadoes streaming from a King Air, a C-130, or a Cessna 210. Wake turbulence is generated by all winged aircraft in flight, including helicopters. A good rule to follow is, big and slow, don't fly below. The most successful attempt to reduce vortices and induce drag is the winglet. It was developed originally by NASA and has been utilized by several manufacturers. The effect of a winglet is like an extension to the wing, which increases aspect ratio. A higher aspect ratio diminishes the vortices but does not eliminate them. A diminished vortex results in induced drag. If a designer can reduce the tip vortex, he would lower the wing's average angle of attack, thereby reducing induced drag. There is a way to do this. It lies within the ratio of the wingspan and its chord and is called the aspect ratio. The aspect ratio for a rectangular wing, similar to the ones on many general aviation aircraft, is found by dividing the wingspan by the average chord. A high number would indicate a long, narrow wing, such as those used on high-performance sailplanes. This kind of wing is desirable for aircraft which need, where speed is not an overriding requirement, but climb and cruise performance are. The key to a lower induced drag on a high aspect ratio wing is the distance between the tip vortex and the wing root. Although its effect is felt along the entire wing, the energy of the vortex is dissipated with distance. Theoretically, a wing with an infinite span would have no induced drag. It would be easy for us to assume that a long, slender wing would be the best wing for general aviation aircraft. However, consider that this long, slender wing would be subject to more bending and twisting forces, so it would have to be beefed up internally. The added weight would so reduce performance that there would be no real gain over a shorter wing. There are other reasons as well, one of these being simple ground handling and storage. The designer is faced with one more compromise in putting together the ideal wing for his plane. The formula for determining drag forces is similar to that for lift. Drag is equal to the coefficient of drag times the dynamic pressure times the wing surface area. As in other equations used in aerodynamics, a coefficient is a dimensionless index designed to correct the mathematical process. In this instance, the coefficient of drag is a number which measures how a particular wing develops induced drag at various angles of attack. It would be great if a low coefficient of drag could be associated with the high lift coefficient. Unfortunately, the two increase in value together. We have discussed parasite and induced drag for a while now. Let's see how they compare in their effects on an airplane. Our first consideration is mathematical. Parasite drag varies directly as the speed is squared, while induced drag varies inversely as the speed is squared. The implication is that as an airplane moves faster through the air, the parasite drag builds up rapidly while the induced drag decreases. As the aircraft approaches for a landing, the induced drag increases rapidly while the parasite drag diminishes. A pocket calculator will show how rapidly parasite drag can build. Let's take a plane which develops 100 pounds of parasite drag at 100 miles per hour. We double the speed of the airplane to 200, but parasite drag varies as the square of the speed. This means that now we are producing 400 pounds of parasite drag. Remember that while this is going on, the induced drag has been reduced by the square of the speed. An illustration at this point might help visualize this relationship better. This graph contains the parasite drag curve, the induced drag curve, and the curve for total drag. It is easy to see that as one drag force decreases, the other increases. For practical purposes, the total drag becomes the important curve on the graph. In interpreting this graph, if we assume that the aircraft is producing lift equal to 1g, or the weight of the plane, the lowest point, point A, total drag curve, would give the least amount of drag relative to lift. This point would give the highest lift to drag ratio. The airspeed at the point where induced drag and parasite drag are equal will give this plane its maximum range and also its maximum power-off gliding range. The maximum lift to drag ratio for a given aircraft is established at a fixed angle of attack. On your airplane, the maximum range would occur if you always flew it at the same angle of attack regardless of weight. However, weight will vary, so something must give, and that is airspeed. For maximum range, you would maintain an angle of attack and decrease airspeed as fuel burned off and lighten the aircraft. If you were flying a single-engine aircraft 10,000 feet above the surface and had a power failure, how far would you be able to glide before landing? The answer lies with the angle of attack, which will produce the highest lift-to-drag number. For a hypothetical airplane, a given angle of attack could produce a lift-to-drag number of 10. This is a glide ratio of 10 to 1. You could glide almost 20 miles from that altitude, provided you maintain proper angle of attack. Your airspeed would depend upon the weight of the plane. The trouble with this idea is that we don't have a good, inexpensive angle of attack indicator. You don't ever know what the angle of attack is at a given time. The best substitute is a chart giving the lift-to-drag numbers at various airspeeds and weights. Most aircraft operating manuals will give a range charts or graphs in the performance section. Although they seldom mention the lift-to-drag numbers, the charts are based on calculations from the lift-to-drag ratios. There are a couple of other figures which you can obtain from a chart of drag curve. A plane's range and endurance are not the same. By slowing the airspeed further, you can keep the plane in the air longer. A rule of thumb might be, if you know the maximum range and maximum gliding range airspeeds of your plane, you can calculate 75% of that figure. You now have the maximum endurance speed. It's pretty slow, but it will keep you in the air longer, if time is more important than distance. No one is going to give you a medal for the most turns made in a holding pattern. The maximum endurance airspeed is at a point where induced drag is creating 75% of the total drag. Keep in mind that it is really a specific angle of attack rather than an airspeed, but for the lack of anything better, we must go with airspeed. One more thing about the airspeed for maximum endurance. It is also the airspeed which will give you the least power-off sink rate. So, for that forced landing due to engine trouble, if your chosen field is under you, you may want the slower speed to give more time for communications and setting the plane up for landing. Certainly you would want to consider minimum sink on a night forced landing. There is another curve which can be plotted on a graph which is related to the drag curve. Although it is overlooked in many basic training manuals and by many flight instructors, the information it presents is very important to those who fly. The graph I refer to is the power required curve, which includes information on the flight in the region of reverse command. At first glance, you will see that the power required curve resembles the curve for total drag. That is only natural, since thrust equals drag in order to maintain a given airspeed. However, thrust and power are not quite synonymous. Power is the work turned out by the engine, which it transmits to the propeller, which in turn converts the energy to thrust. In the process, there is some loss of energy, especially at the extremes of airspeed. This is indicated by the power available curve near the top of the chart. The horizontal lines represent percent of brake horsepower, and the vertical lines represent indicated airspeed. The curve begins on the left at the stall speed and ends on the right at the end of the power available line. To the right of the vertical line, through point D, is the region of normal command, or what we call the front side of the power curve. To the left of the vertical line is the region of reverse command, or the back side of the power curve. Consider point D first. It is located at the lowest point of the curve, where the power requirement and consequently fuel consumption are at a minimum. This point represents the requirements for maximum endurance and minimum sink glide. At this point, any change in the angle of attack will produce a loss of altitude if power is constant. Point CC is located at the place where a line from the origin of the graph touches the curve as a tangent. This represents the maximum range and maximum gliding range requirements. The significance of this location is that there is a large increase in airspeed at only a slight increase in the power required. At point AA, the pilot is using full power available to maintain maximum airspeed. As at point D, any change in angle of attack will cause a loss in altitude. There is no more power to compensate for a higher angle of attack, so the plane will descend. Lowering the angle of attack will give you increased airspeed, but it will come at the expense of altitude. At any point on the front side of the curve, an increased angle of attack will slow the aircraft and it will climb. A decreased angle of attack will increase speed and cause a loss of altitude. This is what you expect as you fly, and this is why it's called the region of normal command. You will note that for every power setting necessary to maintain a given airspeed on the front side of the power curve, there is an identical power setting required to maintain a much lower airspeed on the back side of the power curve. It is a fact that while in the region of reverse command, the slower you fly, the more power it takes to maintain altitude. This is due to the power of induced drag while the wing is at high angles of attack. Let us assume that the airplane at point C is on a long, power-on final in a busy traffic pattern at an airport with training activities. His airspeed is 73 and he is using 50% of power. Any nudge from his current angle of attack will produce results reversed from normal. Let's suppose this pilot lets the nose drop a little due to some gustiness close to the ground. The airspeed will pick up, but the aircraft's inherent stability will not automatically correct for the extra speed. Unless the throttle is retarded, the plane will momentarily retain the additional airspeed and will climb. Climb with the nose down? That is correct. Remember, we are now in the region of reverse command. Now, let's try to put it another way. The nose of the plane at sea up a bit. The airspeed slows a bit, and the plane begins to sink. The pilot raises the nose a little more and adds some power to regain his approach speed of 73. At this point, 73 is no longer enough. The increased angle of attack has added a large amount of induced drag, which is acting just like a drag chute. The only cure at this point is a lot of power and a lower angle of attack. If the pilot continues to maintain his approach by increasing his nose-high attitude, he will probably mush into the ground short of the runway. It could even happen with the throttle wide open under certain circumstances. Pilots don't get in trouble with the region of reverse command at cruising altitudes because it only occurs at the slower speeds, and these problems are usually on takeoff or landing. One situation which bends a few planes every year is the go-around with full flaps. This is because the flaps have added a tremendous amount of induced drag and the backside of the power curve has been expanded. It is important in this instance that no climb be attempted until you have determined what a higher angle of attack will actually give you in terms of a climb. Retraction of flaps must be done very slowly and only when there is sufficient altitude to absorb a loss of lift as the flaps come up. Flaps must come up slowly so that the acceleration of the plane has time to compensate for the loss of lift. There is another phenomenon associated with induced drag which can be good or bad depending on how familiar you are with it. It's called ground effect. First, let me tell you what it is not. It is not a cushion of air that forms between the wing and the ground. This myth has been around for many years and has been responsible for many pilots getting into trouble. We discussed previously how updrafts, downdrafts, and vortices form around a wing in motion. You know from that discussion that a portion of the lifting force produced by the wing is directed aft and is referred to as induced drag. As the angle of attack and coefficient of lift increase, so does the induced drag. Induced drag is at its greatest when your plane is slow at a high angle of attack. Suppose that we could eliminate some of the vertical vortices which develop ahead and behind the wing. This would lower the average relative wind and place the chord a little more parallel to the ground. If we could do this, the aft component of lift force, which we call induced drag, would not be as great, but instead would produce a slight increase in the effective lift. That is precisely what ground effect does. If there is no cushion of air, how does this happen? The vertical movement of air around a wing disturbs the air at considerable distance from the wing surface. The vertical distance from this disturbance is roughly the span of the wings. Suppose that your plane has a span of 36 feet and that you're flying that plane 36 feet above the ground. The downwash should have some effect on the blades of grass below you. By descending even further, something has to happen to the downwash. It flattens out because it has no place else to go. The closer to the ground you fly, the more restricted are the vertical velocities behind the wing. At wingspan height, you will lose about 2% of the induced drag. At half the wingspan, you have eliminated about 8% of the induced drag. And when you get down to a quarter of the span, you will have eliminated nearly a quarter of the drag. At touchdown, you will have gotten rid of as much as half of the induced drag. Parasite drag, of course, is hardly a factor at speeds we are talking about. All aircraft encounter ground effect, but it is obvious that the effects will be a little greater on low wing types. However, the difference in location of wings doesn't have a large effect, and the suggestions for flying in and out are similar for all types. We all can remember those student landings when you had everything set up and ready for the flare. Then suddenly the plane ballooned up, the nose pitched down, and you floated and floated. You probably had a little excess speed when you entered the ground effect. With less drag to slow us down, we used most of the runway. No touch and go on that one. If you had a good instructor, he would have taken the time during the taxi back to explain why you had used so much runway. I haven't mentioned the tendency for the nose to pitch down in our earlier explanation of ground effect. Planes are designed to be slightly nose heavy. The downwash affecting the horizontal stabilizer is used to counteract this nose down pitch. The purpose of this is for stability, which will be discussed more fully in another presentation in this series. We know then that it is necessary for the horizontal stabilizer to have the downwash in order for it to be effective. In ground effect, the downwash is diminished, allowing the nose to pitch down. This means that upon entering ground effect, you will have to use more elevator. A full stall landing will take considerably more elevator than a normal power-off stall at any altitude. The place where ground effect has caused the most trouble is on takeoff. Most of us were taught to make good use of it during the soft field takeoff. It is also put to good use by many duster pilots and others who regularly fly with maximum gross loads. But for those who don't understand ground effect fully, it can be disastrous. The typical situation is a fully loaded aircraft attempting a takeoff on a hot day. The pilot senses that he is taking more runway than usual, so he horses it into the air at a high angle of attack. He forgets that those first few feet of altitude are high in lift but lower in drag. By the time he is 25 to 30 feet off the runway, some of the original lift has been converted to drag. At this point, the pilot is committed. His runway has been used, and he is 30 feet off the runway behind the power curve. He has no more power to call for and a high angle of attack, which can only cause him to sink. The only real choice for him is to keep from stalling and put the plane down on whatever surface lies off the end of the runway. The elevator response upon leaving ground effect is the reverse of that on landing. Downwash is established as the ground effect diminishes, which puts the horizontal stabilizer back to work. However, you have been using excessive elevator to compensate while you were in ground effect. Upon leaving ground effect, the airplane will pitch up due to too much elevator control. If you were in marginal flight at that time, you could fly right into a stall. The negative consequences of ground effect are quite dramatic. However, you fly in and out of it each time you take off or land. So does everyone else. If you know why it happens and how to deal with it, your landings and takeoffs will continue to be successful. Lift and drag. These are the chief ingredients for the study of aerodynamics. Let's review what we have done. The first thing we did was to define parasite drag and to list all of the elements in its makeup. They were form, skin friction, interference, separation, pressure field, power plant, and wing section profile drag. Next, we spent time analyzing the factors which create induced drag. We compared parasite and induced drag and discovered that when one was weak, the other was powerful. We discussed the wing's aspect ratio and the lift-to-drag ratio. Much of the material in the first part of the presentation became applicable when we discussed the region of reverse command, or what is sometimes called getting behind the power curve. Our final discussion dealt with the lack of drag. It was about ground effect and how to deal with it. This concludes this presentation on the development of drag. My name is